Good morning, professors. We are from St. Paul's Coeducational College. The challenge of generalizing notions and results in Euclidean geometry in the plane to higher dimensions has attracted numerous mathematics lovers to work on. One primary direction of generalization is of triangles to simplices, and investigating how much geometry can or cannot be carried over. As a continuation of our school's HRMA 2018 research, which focused on tetrahedron centers, our current paper, Generalizing Orthocentres of Triangles to Simplices as the Isogonal Conjugates of the Circumcentres, has constructed a new generalization of the orthocenter to Euclidean simplices using isogonal conjugation. This presentation is organized as follows. First, we will discuss the background which has motivated our research. Then, we will discuss our method of generalizing the idea of isogonal conjugation from triangles to simplices. Finally, we will discuss two interesting properties of the isogonal conjugates of the circumcentres of simplices. Our research began with having learned the oddity that the orthocenter of a simplex may not exist, because the altitudes may not be concurrent, as shown in this diagram. The so-called Monge point, antimedial circumcenter, and orphic inexcenter have generalized the orthocentres of triangles to tetrahedra or simplices from quite distinct perspectives. They were invented through focusing on alternative defining properties of the orthocenter of a triangle rather than using altitudes, and each of them preserves a portion of the properties of the orthocenter of a triangle. Our focus is on the following defining property. The orthocenter H of a triangle is the isogonal conjugate of the circumcenter O of the triangle, which means that O and H incline equally from the sides of the triangle. The next slide shows the classical definition of isogonal conjugation in a triangle. Given a triangle ABC and a point P in general position, there exists a unique point P star such that these two red angles, these two blue angles, and these two green angles are equal as shown. P star is called the isogonal conjugate of P with respect to triangle ABC. However, in higher dimensions, dihedral angles are rather clunky and hard to work with. We have developed other characterizations of points being equally inclined from two facets of a simplex. Before we discuss our main results, we will explain the notations that will be used throughout. In our work, delta denotes our n-dimensional reference simplex. V0 to Vn denotes the vertices of delta. Fi denotes the extended facet opposite to Vi, and Fij denotes the intersection of Fi and Fj. D of P, H denotes the distance from point P to hyperplane H, and if H is an extended facet of delta, we will attach a plus or minus sign to denote the inward signed distance from P to H, which is positive if P lies on the side of H containing delta, and negative if P lies on the other side. Xi denotes the projection of X on Fi, and Xi prime denotes the reflection of X across Fi. Our first main result is lemma 13, which describes new characterizations for 2 points X and Y being equally inclined from two extended facets Fi, Fj in 5 equivalent conditions. A. The reflection X prime of X across the angle bisector Bij of Fi and Fj lies on a hyperplane containing Y and Fij. B. The product of the signed distances from X and Y to Fi is equal to the corresponding product to Fj. C. Recall that Xi prime and Xj prime are the reflections of X across Fi and Fj. This condition says that they are equidistant to Y. D. If Xi's and Yi's are the barycentric coordinates of X and Y with respect to the vertices Vi's of the simplex, then this equation holds. In the case where X and Y are both interior points, we have condition E, that the hyperplane AX containing X and Fij and the hyperplane AY containing Y and Fij are equally inclined from Fi and Fj. Applying this lemma to all pairs of facets gives us our second main result, theorem 14, which gives 5 equivalent conditions for isogonal conjugate pairs. A. For each pair of facets, the reflection of X across the angle bisector Bij lies on a hypersphere containing Y and Fij. B. The product of signed distances from X and Y to each facet are all the same. C. all the reflections xi primes are equidistant to y. And condition D is this equation in using barycentric coordinates. And in the case where x and y are interior points, we have condition E, x and y are equally inclined from each pair of facets, fi and fj. Condition E is actually the very definition of isogonal conjugates for interior points given in a 2017 paper named Isogonal Conjugates in an N-simplex. Our theorem 14 has extended the scope to non-interior points, as conditions A to D are not restricted to interior points x and y. In regard to our extension of isogonal conjugation to non-interior points, our theorem 16 completely classifies all cases of isogonal conjugate pairs. A. If x lies on some of the extended facets, then y forms an isogonal conjugate pair with x if and only if y lies on the intersection of the remaining extended facets. In such case, many y form isogonal conjugate pairs with x, or many x form isogonal conjugate pairs with y. B is if x does not lie on any of the facets, and the following sum evaluates to 0, then no points form an isogonal conjugate pair with x. In both cases, we say that the isogonal conjugate of x does not exist. Otherwise, there is a unique point x star which forms an isogonal conjugate pair with x, and x is also the unique point which forms an isogonal conjugate pair with x star. We say that x star is the isogonal conjugate of x with barycentric representation as shown. We close this section with the following generalization of a well-known result from 2D. Theorem 17. For 2 points x and y forming an isogonal conjugate pair, their projections, xi's and yi's on all the extended facets, 2n plus 2 points in total, all lie on a common hypersphere whose center is the midpoint of x and y. Here comes the last section of this presentation. Mentioned in the beginning, the orthocenter of a triangle is also the isogonal conjugate of the circumcenter. Our research has largely been devoted to studying its higher dimensional analog. Recall that the circumcenter O of a simplex is the unique point equidistant to all its vertices. Note that O does not necessarily have an isogonal conjugate O star, but when O star exists, it has the following two intriguing properties. Firstly, O star is an index center of its own pedal simplex. Here, an index center of a simplex is a point which has equal distance to all the facets. And the pedal simplex of O star refers to the simplex whose vertices are the projections of O star onto the extended facets. Moreover, in the case where O star is inside the simplex as shown, it is actually the in-center of its own pedal simplex, and also is the only interior point with this property. Here, the in-center of a simplex is the unique point which has equal signed distances to all the facets of the simplex. To state our last result, we need to introduce the higher dimensional analogs to two plane geometry notions. 1. For a hypersphere S with center O and radius r, the power of a point x to S is defined as the length of OX squared minus r squared. In 2D, the radical axis of two circles is defined as the locus of points having equal powers to the two circles, and the radical center of three circles is the unique point having equal powers to the three circles as shown. In general dimension, we can define the radical hyperplane of two hyperspheres, which is the locus of points having equal powers to the two hyperspheres. And we can define the radical center of a set of hyperspheres similarly. 2. The facetal circumhypersphere Si of a facet Fi is defined as the hypersphere centered at the circumcenter of Fi and passing through all of the vertices lying on Fi. Our final theorem 27 states that O star is the radical center of all the facetal circumhyperspheres. In other words, it is the unique point having equal powers to all the facetal circumhyperspheres. This concludes our presentation, which has delivered how we have extended the notion of isogonal conjugation from triangles to simplices, as well as generalizing three well-known plane geometry results from triangles to simplices via isogonal conjugation. Thank you.